Hello, welcome again. We are covering the subject compressible fluid flow for civil services MECH, IFS and Gate Aerospace exam. So we are discussing the topic effect of pressure ratio for a given load. And we have studied in the last video that this is the isentropic condition to achieve Mach number m. If that PE pressure is maintained at the exit of the nozzle, then this Mach number according to area ratio can be obtained in the nozzle. Okay, and this is your design condition. So now if this pressure is not maintained at the exit of the nozzle, then these are called off design conditions. Okay, and these off design conditions can be obtained by varying the back pressure, which in turns vary exit pressure. So back pressure is the pressure of the reservoir to which the exit of the nozzle is connected. If we vary the back pressure, then exit pressure will automatically vary. Okay, so now we'll discuss these off design conditions one by one by reading out this paragraph or the points and explaining this. Consider a convergent divergent nozzle as shown in figure 8. Assume that no flow exists in the nozzle, hence PE is equal to P naught. Suppose this is your nozzle and here the stagnation conditions are maintained, approximately stagnation conditions are maintained, so that we can assume stagnation pressure here, and here we can assume A by A star as infinity. A star is the reference critical area for any nozzle for particular conditions. So A by A star here is your infinity, and this is your throat area, this is your exit pressure. Now initially P is equal to P naught, and when P is equal to P naught, exit pressure is equal to the inlet pressure, then there will be no flow. Okay. Next line. Now assume that P is minorly reduced below P naught. So now so if we assume that exit pressure is slightly less than P naught, then this is the curve. Okay. So initially this point, this is 1. Initially the exit pressure is equal to this stagnation pressure, that means P by P naught is 1 here, and this is the line. Okay, now when exit pressure is slightly reduced, then this is the curve. Okay, and we can see that here then in this convergent part the pressure reduces up to this throat area, and then pressure increases, so that PE1 is maintained at the exit and ME1 is Mach number achieved. Okay. Now we read this also. Now assume that P is minorly reduced below P naught. This small pressure difference will cause a small wind to blow through the duct at low subsonic speeds. Okay, because pressure is reduced minorly, so the speed will be low subsonic speed. The local Mach number will increase slightly through the convergent portion of the nozzle, reaching a maximum at the throat shown by curve 1 of figure B. This maximum will not be sonic. So here the local Mach number will increase, and this will not be sonic up to throat, and this will increase up to throat, but this will not be sonic. As this is not sonic, so there is subsonic flow, so divergent part will act as diffuser and convergent part will act as nozzle. So here the Mach number will increase, here the Mach number will decrease, so that ME1 will be maintained as the exit. Okay, so this is not the sonic value. The local Mach number will increase slightly through convergent portion of the nozzle, reaching a maximum at the throat shown by curve 1 figure B. This maximum will not be sonic. Indeed, it will be a low subsonic value. Keep in mind that A star is defined earlier is sonic throat area. So as this is not sonic, so This throat area is for that pressure is not your characteristics or A star. Okay, A star, because here A star is defined when the sonic conditions are attained here. Okay, so here the sonic conditions are not attained, so this is not the A star for that pressure. So that is the throat area. Okay, so A star is the reference quantity for that pressure. The A star will be less than this 80. Okay, so will not, indeed it will be a low subsonic value. Keep in mind that A star is defined earlier is the sonic throat area. That is the area where m is equal to 1. In this case we are considering m less than 1 at the minimum area section of the duct. The real throat area of the duct 80 is larger than A star, which for completely subsonic flow takes on character of a reference quantity different from the actual geometric throat. So this is your throat area, throat the critical area, which is your reference quantity for sonic velocity, sonic flow to exist. So as if we assume that our nozzle is like that, this is convergent part, and convergent part slightly further extended, somewhere is sonic velocity will exist. So that A star is your characteristic area for that pressure. Now for that pressure, this is not the A star, this is larger than the A star. Okay. Next point, downstream of the throat, the subsonic flow encounters a diverging section and hence m decreases as shown in figure B. The corresponding variation of the static pressure is given by curve 1 of figure C. So here downstream, as this is the subsonic case, so inlet to the divergent duct is your subsonic, so it will decrease the MECH number. Next point, now assume PE is further reduced. This stronger pressure ratio between inlet and exit will now accelerate the flow more, and variation of subsonic MECH number and static pressure to the duct will be larger as indicated by the curve 2 in the figure B and C. So now if we further reduce the pressure, then we will get increased MECH number at exit, but still the sonic conditions are not achieved at the throat. So this is for curve 2, and this is the pressure variation for curve 2. Now next point, if P is further reduced, there will be some value of P at which the flow is just barely go sonic at the throat, as given by the curve 3 in figure B and C. In this case, AT is equal to A star. Now if the pressure is further reduced, suppose we reduce pressure up to P3, then the sonic conditions are achieved at the throat, but here the pressure is not reduced to that extent that the supersonic velocity can be achieved. Here still the flow is subsonic. So we have reduced the pressure and attained the subsonic conditions and attained the sonic condition at the throat, that is corresponding to P3, and for air this pressure ratio at the throat is 0.5 to 8.